There's something hauntingly beautiful about a black hole, a place where the universe bends the rules so dramatically that even light can't escape. Picture it, a swirling vortex of darkness, so dense and powerful it warps space-time itself, pulling everything into its grasp. But what if these cosmic monsters aren't just destroyers? What if they're also messengers, whispering secrets about the very soul of matter? Welcome to Hearts of Darkness, where we'll explore how black holes reveal the hidden threads stitching reality together. This isn't just about gravity or collapsed stars. It's about peering into the abyss and discovering what it tells us about existence itself. Think about the last time you stood under a starry sky, feeling small yet connected to something vast. Now imagine that feeling amplified 1,000 times, because black holes don't just challenge our place in the universe, they challenge our understanding of reality. What happens to matter when it crosses the event horizon? Does it vanish, or is it transformed? Scientists have grappled with these questions for decades, but the answers might hold clues to something even grander: the nature of time, the fabric of space-time, and whether the universe has a hidden blueprint we're only beginning to decode. This journey will take us from the mind-bending physics of singularity to the eerie quantum whispers at the edge of a black hole's shadow. We'll unravel how these enigmatic objects force us to rethink everything from Einstein's theories to the very meaning of nothingness. And along the way, we'll confront a tantalizing possibility: that black holes aren't just cosmic oddities, but windows into the deepest layers of existence. So buckle up, because by the end, you might never look at the night sky the same way again. The darkness isn't empty, it's alive with mysteries waiting to be uncovered. To understand black holes, we have to start with the death of a star. When a massive star, many times heavier than our sun, burns through its fuel, the outward pressure of nuclear fusion can no longer hold back the crushing weight of its own gravity. The star collapses in on itself in a cataclysmic explosion called a supernova, leaving behind an unimaginably dense core. If this core is heavy enough, nothing can stop its collapse, not even the fundamental forces that hold atoms together. The result: a black hole, a region of space where gravity is so intense that it warps the very fabric of reality. At the heart of every black hole lies the singularity, a point where all the collapsed matter is compressed into an infinitely small, infinitely dense space. Surrounding it is the event horizon, the infamous point of no return. Picture standing at the edge of a waterfall where the current grows too strong to swim against. That's the event horizon, except instead of water, it's gravity pulling with such force that not even light, the fastest thing in the universe, can escape. Once something crosses that boundary, it's gone from our observable reality forever. But what happens to objects unlucky enough to get too close? They undergo a process called spaghettification, yes, as ridiculous as it sounds. Imagine falling feet first toward a black hole. The gravitational pull on your feet would be so much stronger than on your head that you'd be stretched into a long, thin strand like cosmic pasta. Even stars aren't spared when they wander too close. They're torn apart in spectacular tidal forces, their material spiraling into the black holes more like water circling a drain. Yet black holes aren't entirely dark secrets. Thanks to Stephen Hawking, we know they emit faint radiation, Hawking radiation, slowly leaking energy over unimaginable stretches of time. This means black holes aren't eternal. They evaporate, though it would take far longer than the current age of the universe for even a small one to disappear. So why does this matter beyond cosmic spectacle? Because black holes push the laws of physics to their limits. They're cosmic laboratories where matter, space, and time behave in ways we can't replicate anywhere else. And hidden in their extreme conditions might be answers to some of the biggest mysteries, like what truly happens to information that falls in, or whether space-time itself has a deeper structure waiting to be uncovered. The more we learn about these dark hearts, the more they illuminate the invisible rules shaping everything around us. Einstein's theory of general relativity didn't just redefine gravity, it ripped open the cosmic rulebook and rewrote it entirely. Before his groundbreaking work, scientists saw gravity as a simple force pulling objects together. But Einstein imagined something far more radical. Gravity wasn't just a force, it was the bending of space-time itself. Picture a trampoline with a bowling ball at its center. The heavier the ball, the deeper the dip in the fabric. Now replace the trampoline with the fabric of the universe and the bowling ball with a star, or better yet, a black hole. That's the essence of general relativity. Massive objects don't just attract things, they warp the very stage on which the universe plays out. It was this revolutionary idea that led to the first mathematical prediction of black holes, though Einstein himself never believed they could actually exist. In 1915, his equations revealed that if enough mass were squeezed into a small enough space, space-time could curve so severely that nothing, not even light, could climb back out. The concept seemed so absurd that even Einstein dismissed it as a mathematical quirk, calling black holes too beautiful to be real. But science has a way of humbling even the greatest minds. Decades later, astronomers found evidence of these cosmic anomalies lurking in the darkness, proving that nature had outdone imagination once again. One of the most startling predictions of general relativity is how black holes distort time itself. Near the event horizon, time slows to a crawl compared to the rest of the universe, a phenomenon called gravitational time dilation. If you could hover just outside a black hole's grasp, watching a clock on your spaceship, it would tick normally. But to someone observing you from a safe distance, your movements would appear frozen, as if you were stuck in slow motion forever. This isn't science fiction. It's the universe obeying Einstein's math with eerie precision. Yet for all its brilliance, general relativity isn't the final word on black holes. When we zoom into the quantum scale, where particles flicker in and out of existence, the rules start to unravel. Einstein's equations break down at the singularity, a point of infinite density where the laws of physics as we know them simply cease to function. This clash between the vast and the vanishingly small is one of science's greatest unsolved puzzles. If general relativity paints black holes as smooth, warped landscapes, quantum mechanics suggests they might be chaotic, seething with particles popping into being at their edges. So which is it? The answer might lie in the whispers of Hawking radiation, or in the holographic principle, which hints that everything swallowed by a black hole could be encoded on its surface like a cosmic fingerprint. The tension between these two theories, general relativity's cosmic ballet and quantum mechanics' subatomic chaos, is where the next chapter of black hole science begins. If we can reconcile them, we might finally crack open the universe's deepest secrets. After all, black holes aren't just cosmic dead ends, they're gateways to a new understanding of reality itself. Black holes are where the universe's rulebook gets torn in half. On one side, you have general relativity, Einstein's masterpiece, describing gravity as the graceful warping of space-time. On the other, quantum mechanics, the bizarre but bulletproof framework governing the subatomic world, where particles blink in and out of existence and reality, is fundamentally fuzzy. Both theories work flawlessly in their own domains, but near a black hole's singularity, they clash violently, like two languages shouting over each other with no translator in sight. Take the infamous information paradox. Quantum mechanics has a sacred law. Information can never be truly destroyed. If you burn a book, the ashes and smoke still hold traces of its words, just scrambled. But black holes seem to break this rule. When matter falls in, it's crushed into oblivion at the singularity, leaving no trace behind except mass, charge, and spin. Even Hawking radiation, the faint glow black holes emit, appears random, carrying no fingerprints of what was swallowed. So where does the information go? Does it vanish, violating quantum law, or is it somehow preserved in a way we can't yet see? This puzzle led to some mind-bending theories. The holographic principle suggests that everything falling into a black hole isn't lost. It's encoded on its event horizon, like a cosmic DVD storing 3D data on a 2D surface. Imagine dipping your hand into a pool. The ripples it creates don't contain your hand, but they reflect its shape and motion. Similarly, a black hole's surface might holographically preserve the information of whatever crosses its threshold. Then there's the firewall paradox, which cranks the weirdness even higher. If quantum mechanics is right, the event horizon shouldn't feel special, just empty space. But calculations show it might instead be a searing wall of energy, incinerating anything that touches it. Picture walking toward what looks like a calm fog, only to realize too late it's a curtain of flame. This idea horrified physicists because it meant Einstein's smooth spacetime near the horizon was an illusion replaced by quantum chaos. So why does this cosmic tug of war matter? Because black holes force us to confront the limits of our understanding. If we can crack how information escapes, or if it never truly falls in, we might uncover the hidden grammar stitching reality together. These contradictions aren't flaws in the universe, they're breadcrumbs leading to something deeper, and the wildest part, the answers could rewrite not just how we see black holes, but how we see everything. The holographic principle sounds like something ripped from the pages of a sci-fi novel, but it might just be the universe's best-kept secret. Imagine your entire reality, every star, every galaxy, even the device you're watching this on, isn't truly three-dimensional. Instead, it's a projection, like a hologram on a credit card. That shimmering 2D surface contains all the information needed to recreate a 3D image when light hits it just right. Now stretch that idea to cosmic scales. What if the universe works the same way? What if everything we see, touch, and experience is just a shadow cast by information scribbled onto a distant, flat boundary we can't even perceive? This wild idea didn't come from nowhere. It sprouted from the thorny soil of black hole physics. Remember the information paradox. If black holes swallow matter but information can't vanish, where does it go? The holographic principle offers a jaw-dropping answer. It never actually falls in. Instead, every particle, every shred of data about what's inside a black hole gets smeared across its event horizon like ink on a cosmic parchment. The surface area of the horizon becomes a ledger, recording everything that crossed it in intricate, invisible detail. Think of it like a detective reconstructing a crime scene from security camera footage. The camera's 2D image doesn't contain the 3D room, but it holds enough clues to rebuild it. Similarly, the event horizon's fluctuations might encode the entire interior of the black hole. This isn't just poetic speculation. The math checks out. Physicists have shown that the amount of information you can pack onto a region of space doesn't depend on its volume, the 3D bulk, but on its surface area, the 2D boundary. It's as if the universe has a hidden compression algorithm, squeezing 3 dimensions into 2 without losing a single byte. Now here's where it gets even stranger. If this principle holds for black holes, why stop there? Some theorists argue the entire universe could be a hologram. The space around us, with its galaxies and gravity, might just be the projected image of data stored on some unimaginably distant, flat surface a cosmic screen will never see. It's like living inside a bubble where every event, every atom is a pixel illuminated by a deeper layer of reality. What does this mean for the soul of matter? If the holographic principle is true, then the solid, tangible world we experience is an illusion, a performance staged by underlying information. Matter isn't the foundation of reality, information is. The electrons in your phone, the neurons in your brain, even the black holes devouring stars could all be manifestations of data dancing on a hidden surface. This flips our understanding of existence upside down. Instead of asking what the universe is made of, we might need to ask, what is it computing? The answers could rewrite not just physics, but philosophy itself, blurring the line between the material and the metaphysical in ways we're only beginning to fathom. If you could hover just outside a black hole's event horizon, close enough to feel its gravitational pull but not so close that you're doomed, you'd witness one of the universe's strangest magic tricks, time itself bending under the weight of extreme gravity. This isn't science fiction, it's a direct consequence of Einstein's general relativity. The closer you get to a black hole, the slower time ticks for you compared to someone watching from a safe distance. Picture a clock strapped to your wrist as you descend toward the abyss. To you, it would seem normal, but to an observer far away, your movements would stretch out like molasses, your seconds becoming their minutes, then hours, then years. You might experience mere hours near the horizon while centuries pass back on Earth, a one-way trip into the future. This phenomenon, called gravitational time dilation, isn't unique to black holes. Even Earth's gravity causes it, though on a microscopic scale. GPS satellites orbiting our planet have to account for tiny time discrepancies caused by their distance from Earth's gravitational pull. But near a black hole, the effect is so extreme it warps reality itself. For an astronaut foolish enough to dive in, time would slow to a crawl as they approached the event horizon. From their perspective, they'd cross the threshold in finite time, but to the outside universe, they'd appear frozen there forever, their image redshifted into oblivion as space-time stretches their final moments across eternity. Now here's where it gets even weirder. If time grinds to a near halt at the event horizon, what happens inside? Some theories suggest that within a black hole, time and space swap roles. The singularity, the point of infinite density at the center, isn't just a place, it's a moment. Once you cross the horizon, all paths lead inexorably toward it, just as all paths in our everyday world lead forward in time. You can no more avoid hitting the singularity than you can avoid tomorrow's sunrise. In this twisted realm, the singularity might represent the literal end of time for anything that falls in. This raises a haunting philosophical question. If time stops at the singularity, does that mean the laws of cause and effect break down? Is the interior of a black hole a place where physics as we know it ceases to have meaning? The equations of general relativity scream yes, but nature abhors a paradox. Some physicists speculate that quantum effects might prevent true singularities from forming, replacing them with a fuzzy, seething quantum foam where space and time lose all semblance of order. Others propose that black holes are cosmic Rosetta Stones, their interiors encoding a deeper relationship between time and matter. Because here's the profound connection. Time isn't just a backdrop for the universe, it's woven into the fabric of matter itself. The same gravitational forces that warp time near a black hole also dictate how particles interact, how stars burn, and how galaxies spin. If black holes stretch time like taffy, they're revealing something fundamental about how matter experiences reality. The iron in your blood, the silicon in your phone, even the light from your screen, all of it carries traces of this cosmic dance between time and substance. So when we peer into the abyss, we're not just studying distant monsters, we're holding up a mirror to the very essence of existence. At the heart of a black hole lies the singularity, a point where all the rules we thought governed the universe crumble into nonsense. Imagine taking the entire mass of a collapsed star, squeezing it past the point of atoms, past protons and electrons, until it occupies zero volume. The density becomes infinite, gravity spirals toward impossibility, and space-time itself fractures like glass under too much pressure. This isn't just extreme physics, it's where physics ends. Mathematically, singularities are inevitable in Einstein's equations, the unavoidable conclusion when too much mass collapses into too little space. But mathematics and reality don't always agree. We've never observed a singularity directly, and we likely never will. The event horizon shrouds it like a cosmic veil, hiding the chaos within. Even if we could send a probe inside, it would be torn apart long before reaching the center, its final signals stretched into gibberish by the black hole's gravitational grip. So are singularities real, or are they just flaws in our theories? Some physicists argue they're mathematical mirages, revealing where general relativity fails to account for quantum mechanics. After all, nature abhors infinity. In the quantum world, particles can't occupy the same space without resistance. The uncertainty principle forbids it. Perhaps the singularity is a signpost pointing toward a deeper theory, one that blends gravity and quantum behavior into a unified framework. This is where dark matter, the universe's ghostly scaffolding, might hold unexpected clues. Though dark matter doesn't interact with light, its gravitational influence is everywhere, shaping galaxies and bending space-time in ways we're only beginning to map. Could it play a role in what happens at the singularity? Some speculative models suggest dark matter's peculiar properties might soften the infinite density, replacing the singularity with something stranger, a quantum knot, a ripple in higher dimensions, or even a doorway to another universe. The singularity forces us to confront the limits of human knowledge. It's a cosmic question mark, daring us to look beyond Einstein's equations and into the unknown. Whether it's a flaw or a gateway, one thing is certain: the answers won't come from staring into the darkness. They'll come from rewriting the rules of reality itself. Dark matter and black holes might seem like unrelated cosmic mysteries, one an invisible glue holding galaxies together, the other a gravitational monster tearing spacetime apart. But what if they're two sides of the same coin? For decades, scientists have puzzled over dark matter's true nature. It doesn't emit light, reflect it, or interact with ordinary matter in any way except through gravity. Yet its presence is undeniable, sculpting the universe's large-scale structure like an unseen hand. Meanwhile, black holes defy our understanding in their own right, warping reality to its limits. Could these enigmas be connected in ways we're only beginning to grasp? One tantalizing theory suggests that some, or even all, dark matter could be made of primordial black holes. These wouldn't be the black holes we know, born from dying stars. Instead, they'd be relics of the early universe, forged in the seething chaos of the Big Bang itself. Picture the cosmos moments after its birth, a dense, bubbling soup of energy. Tiny fluctuations in density could have collapsed into micro black holes, some no heavier than a mountain yet as small as an atom. Unlike their stellar counterparts, these ancient objects would have evaded detection, drifting through space like invisible ghosts. They'd exert gravitational pull without emitting light, matching dark matter's elusive profile perfectly. But how would we find them? Some clues might lie in gravitational microlensing, a cosmic magnifying effect where a massive object bends light from a distant star. If a primordial black hole passed between us and that star, its gravity would briefly amplify the starlight like a lens. Astronomers have searched for these flickers, but so far the evidence is sparse. Another clue could come from ripples in space-time. When two primordial black holes merge, they'd send out gravitational waves, subtle tremors detectable by observatories like LIGO. If future instruments catch waves from unusually small black holes, it could hint at a hidden population lurking in the dark. Even if primordial black holes aren't the full answer, black holes and dark matter might still dance together in unexpected ways. Supermassive black holes anchoring the centers of galaxies could act as dark matter traps. Their immense gravity might pull in dark matter particles, concentrating them into dense halos. Some models even suggest these halos could influence how black holes grow, feeding them in ways we can't yet observe. It's a cosmic feedback loop. Dark matter shapes galaxies, galaxies nurture black holes, and black holes, in turn, sculpt the dark matter around them. This interplay raises a profound question. If dark matter truly interacts with black holes, or even as black holes in some form, does it carry hints about the deeper nature of matter itself? After all, both defy our conventional understanding. Dark matter refuses to engage with the forces that govern atoms, while black holes crush matter into a state beyond our physics. Perhaps their connection isn't just gravitational but existential, pointing toward a hidden layer of reality where the boundaries between matter, energy, and information blur. The answers might not just solve two cosmic puzzles, they could rewrite what we thought we knew about the universe's very fabric. Black holes aren't just cosmic oddities, they're the universe's ultimate testing grounds, places where the laws of physics are pushed to extremes we could never recreate in a lab. Imagine having a natural experiment so powerful it bends space-time, traps light, and crushes matter into oblivion. That's exactly what black holes offer, a front-row seat to the most violent and mysterious processes in existence. And by studying them, we're not just satisfying curiosity, we're piecing together clues that could finally bridge the gap between Einstein's relativity and the bizarre world of quantum mechanics. Take gravitational waves, for example. When two black holes spiral toward each other, their colossal dance sends ripples through the fabric of space-time itself, like tossing a pebble into a pond, except the pond is the universe. In 2015, the LIGO Observatory made history by detecting these waves for the first time, proving Einstein's century-old prediction correct. But the real magic isn't just in confirming the theory, it's in the details. The way black holes merge, the frequencies of their final vibrations, even the echoes of their collisions carry hidden information about the nature of gravity, space-time, and matter under conditions we can't replicate anywhere else. These observations are like cosmic breadcrumbs leading us toward a deeper truth. For instance, when LIGO catches the ring-down phase, the moment after two black holes collide and the newly formed single black hole settles into its final shape, the vibrations match predictions from general relativity almost perfectly. But what if future detectors with even greater sensitivity spot tiny deviations? Those anomalies could be whispers of quantum gravity, hints that space-time isn't perfectly smooth near a black hole's horizon, but instead froths with quantum fluctuations. It's like listening to a bell ringing in a cathedral and realizing the sound isn't quite pure because the bell itself is made of something stranger than metal. And then there's the way black holes challenge our notions of matter itself. Near the event horizon, particles and antiparticles pop in and out of existence thanks to quantum mechanics, with one sometimes falling in while the other escapes as Hawking radiation. This process isn't just a quirky side effect. It suggests that matter and information might be fundamentally linked in ways we don't yet understand. Could the key to unifying relativity and quantum theory lie in how black holes process, distort, or even preserve the stuff that falls into them? Every gravitational wave we detect, every flicker of radiation we observe, is a piece of a puzzle that stretches from the infinitely large to the infinitesimally small. Black holes force us to ask questions that sound like they're from the edge of science fiction. Is space-time pixelated at the tiniest scales? Does the universe holographically encode information on 2D surfaces? And if so, what does that mean for the atoms that make up our bodies, our planet, the stars? The answers won't just rewrite physics textbooks, they'll redefine what we think matter even is. Because when you peer into the heart of darkness, you're not just studying a black hole, you're staring into the soul of the universe itself. Stephen Hawking's greatest breakthrough wasn't just discovering that black holes glow, it was realizing they could fade away entirely. In the 1970s, he made a startling prediction: black holes aren't eternal. Thanks to quantum mechanics, they emit faint radiation, losing energy over unimaginable timescales until they vanish in a final puff of particles. This Hawking radiation rewrote our understanding of black holes, but it also birthed one of physics' most vexing puzzles, the information paradox. If a black hole evaporates, what happens to everything it swallowed? Stars, gas, even entire planets, where does all that information go? According to quantum mechanics, information can never be truly destroyed. Burn a book, and the ashes might seem like chaos, but in theory, you could reverse engineer the process to reconstruct every word. But black holes defy this rule. When matter falls in, it's crushed beyond recognition at the singularity, leaving behind only three clues: mass, spin, and charge. Hawking radiation, the black hole's dying breath, appears random, carrying no trace of what was consumed. So if the hole disappears, the information seemingly vanishes too, a cosmic violation of quantum law. This contradiction haunted Hawking for decades, sparking debates that still rage today. The stakes couldn't be higher. If information is truly lost, it undermines the foundations of quantum theory, forcing us to rethink reality's most basic rules. But if it's preserved, how? One clue might lie in the black hole's soft hair, a poetic term for subtle, low-energy radiation patterns lingering on the event horizon. Think of it like a fingerprint left in the fabric of spacetime. These faint imprints, proposed by physicists like Andrew Strominger, could encode details about what fell in, acting as a quantum ledger. It's as if the horizon scribbles invisible notes about every passing atom, preserving information in ways we're only beginning to decode. Then there's the holographic principle, which takes the idea even further. If a black hole's interior is projected from data on its surface, like a 3D movie playing on a 2D screen, then information isn't lost, it's transformed. The paradox becomes a matter of perspective. What looks like destruction from the outside might be translation from within, as if the universe has a hidden language we're still learning to read. Resolving this paradox could do more than tidy up physics equations. It might reveal matter's deepest nature. If information survives a black hole's grip, then matter isn't just stuff. It's a dynamic pattern, a kind of cosmic code. The iron in your blood, the silicon in your phone, even the light from your screen could all be manifestations of information woven into space-time itself. Black holes, then, aren't just cosmic garbage disposals. They're encryption machines, scrambling and perhaps unscrambling the universe's secrets in ways we're only starting to glimpse. The answers won't just rewrite textbooks, they'll redefine what it means to exist. String theory offers a radical way to rethink black holes, not as cosmic vacuum cleaners with singularities at their cores, but as swirling tangles of vibrating energy. Imagine the universe's tiniest building blocks aren't particles at all, but infinitesimal strings, each vibrating at different frequencies like the strings of a cello. Pluck one string and you get an electron, pluck another and you get a quark. Now take these strings and knot them together in a dense, frenzied dance. According to string theory, that's what a black hole might really be. Not a point of infinite density, but a vast, vibrating fuzzball of strings, each strand humming with energy and information. This fuzzball theory dissolves the nightmare of the singularity. Instead of matter collapsing into an infinitely small, infinitely dense point, the strings resist being crammed together, forming a fuzzy, extended object with no sharp boundary at its core. Picture a ball of yarn so tangled that every thread touches every other thread, a chaotic yet stable structure where information isn't lost but woven into the very fabric of the fuzzball strings. No singularities, no infinite densities, just a humming, vibrating knot of cosmic data. But here's where it gets even stranger. String theory doesn't stop at replacing singularities. It demands extra dimensions, tiny, curled-up spaces hidden within the fabric of reality. In our everyday world, we experience 3 dimensions of space and 1 of time. But string theory suggests there could be 6 or 7 more, too small to detect directly. Near a black hole's fuzzball, these extra dimensions might unravel, offering a hidden geometry where gravity and quantum mechanics finally shake hands. It's as if the black hole's extreme gravity peels back the universe's surface, revealing a hidden layer where the true nature of matter flickers into view. So what does this mean for the soul of matter? If black holes are fuzzballs, then matter itself might be more than just stuff. It could be music. The vibrations of strings dictate the properties of particles, the forces between them, even the structure of space-time. In this view, the iron in your blood and the light from distant stars are symphonies played on microscopic strings, their harmonies shaping the universe's grand design. String theory's vision of black holes doesn't just solve cosmic puzzles, it redefines reality. If matter is fundamentally vibrational, then black holes aren't just celestial oddities. They are cosmic amplifiers, revealing the hidden frequencies that compose existence itself. And if we listen closely, their whispers might just teach us the universe's deepest melody. What if black holes aren't just cosmic phenomena? What if they're mirrors reflecting the very nature of consciousness itself? It's a wild idea, one that blurs the line between physics and philosophy. But some of the brightest minds in science have dared to explore it. Take Roger Penrose, the Nobel Prize-winning physicist who proposed that consciousness might arise from quantum processes deep within our brains, processes eerily similar to the way space-time warps at the edge of a black hole. His theory, called orchestrated objective reduction, suggests that microtubules in our neurons could harness quantum vibrations, collapsing wave functions in a way that generates subjective experience. And where does this quantum dance happen? In a realm where gravity and quantum mechanics collide, a space not unlike the chaotic frontier of an event horizon. Think of it this way, just as a black hole's event horizon marks the boundary beyond which nothing can escape, our own perception might have its own horizons, limits to what we can observe or comprehend. The universe outside a black hole can't see inside, just as the external world can't directly access the private theater of your thoughts. Could the fabric of space-time and the fabric of awareness share a hidden architecture? It's a dizzying thought, but the parallels don't stop there. Black holes process information in ways we don't fully understand, scrambling it beyond recognition, or perhaps, as the holographic principle suggests, preserving it in coded form. Consciousness, too, is an information processing marvel, weaving sensory input into a seamless stream of awareness, Of course, this isn't to say black holes are sentient. The universe isn't some cosmic brain, and space-time isn't literally thinking, but the structural similarities raise tantalizing questions. If the same quantum gravitational rules govern both the collapse of a star and the flicker of a thought, could studying black holes illuminate the mysteries of the mind? Some researchers speculate that the same physics preventing information loss in black holes might underpin how memories persist in our brains, resisting the entropic march of time. Others go further, suggesting that the universe's tendency to self-organize from galaxies to neural networks might hint at deeper, universal principles binding matter and mind. Still, we should tread carefully. Drawing cosmic metaphors can inspire, but it can also lead to overreach. The gap between a firing neuron and a collapsing star is vast, and conflating them risks muddying both science and philosophy. Yet, even as we temper our excitement with skepticism, the allure of these ideas is undeniable. They remind us that the universe is stranger than we imagine, and that the deepest truths might lie where physics, metaphysics, and sheer wonder intersect. Whether black holes truly hold clues to consciousness or not, they challenge us to think bigger, to see connections where others see only chaos. And in that space between question and answer, science and speculation, we might just find the next great leap in understanding reality and ourselves. Black holes don't just bend space-time, they rewrite the rules of disorder itself. To understand how, we need to talk about entropy, the universe's relentless march toward chaos. Think of entropy as nature's way of mixing things up. Drop cream into coffee and it swirls into randomness, shatter a glass and the pieces scatter irreversibly. The second law of thermodynamics tells us this is unavoidable. In any closed system, entropy always increases, but black holes take this law to its extreme, becoming the ultimate sinks of disorder. When matter falls into one, it doesn't just vanish, it's scrambled into a state of maximum entropy, erased beyond recognition. This revelation came from Jacob Bekenstein, a young physicist who dared to ask a heretical question in the 1970s. What if black holes aren't exceptions to thermodynamics, but its ultimate expression? At the time, most scientists saw black holes as simple, sterile objects defined only by mass, spin, and charge. But Bekenstein proposed they carry entropy proportional to their surface area, specifically the area of their event horizons. The bigger the black hole, the more disorder it contains. This wasn't just a hunch, the math held up. A black hole's entropy, it turned out, was vast. A single one with the mass of our Sun would have an entropy 20 times greater than all the particles in the observable universe combined. Why does this matter? Because entropy is secretly tied to information, the universe's way of keeping score. Every atom, every photon carries data about its state, and when entropy rises, that information doesn't disappear, it just gets harder to read. A black hole takes this to the limit. When a star collapses into one, its structure is obliterated, but Bekenstein's work hinted that the information isn't truly lost. Instead, it's smeared across the horizon, encoded in the microscopic quantum ripples of spacetime. It's as if the black hole becomes a cosmic hard drive, storing data in a language we're still deciphering. This leads us to the arrow of time, the reason we remember the past but not the future. Entropy gives time its direction, and black holes amplify this. Near the event horizon, time dilation stretches moments into eons, but the entropy inside keeps climbing, reinforcing time's one-way flow. Even Hawking radiation, the slow leak of energy from black holes, carries entropy away, ensuring the universe's relentless slide toward disorder. But here's the twist: entropy isn't just about decay, it's about transformation. When a black hole swallows matter, it doesn't just erase it, it reprograms it, like a cosmic alchemist turning lead into something stranger. The iron in a swallowed star, the light from a trapped photon, even the quantum spin of an atom might re-emerge in the holographic hum of the horizon. This reshapes how we see matter itself. The universe isn't just a collection of particles. It's a dynamic, evolving tapestry where entropy weaves the threads. And black holes, they're the looms spinning chaos into something deeper, something that might just hold the key to reality's blueprint. If black holes are the universe's ultimate vacuum, sucking in everything that crosses their path, then white holes are their cosmic opposite, theoretical fountains spewing matter and energy outward with unstoppable force. Picture a black hole in reverse. Instead of an event horizon pulling things in, a white hole has a boundary that nothing can enter, only exit. Matter and light erupt from its core like water from a geyser, blasting into the cosmos with no way to return. It's a mind-bending idea, one that seems ripped from the pages of science fiction, but it emerges naturally from the same equations that predict black holes. In fact, if you rewind the math of a black hole's collapse, you get a white hole, a burst of creation instead of destruction. Could these cosmic fireflies actually exist? Some theories, like loop quantum gravity, suggest they might. This framework proposes that space-time isn't smooth and continuous but made of tiny, indivisible loops like a cosmic mesh. When applied to black holes, loop quantum gravity replaces the singularity with a bridge to a white hole, turning the entire structure into a tunnel between two extremes. Instead of matter vanishing forever, it's reborn on the other side, like a phoenix rising from the ashes. This black hole to white hole transition could happen in mere milliseconds for an outside observer, though for anything falling in, the journey might feel like an eternity due to time dilation. The implications are staggering. If white holes exist, they might explain some of the universe's most violent outbursts, like gamma-ray bursts, flashes of energy so powerful they outshine entire galaxies for brief moments. Imagine a white hole detonating after eons of pent-up pressure, ejecting jets of radiation at near light speed. These explosions could be the universe's way of recycling, turning the devoured into the delivered. Yet for all their theoretical elegance, white holes face a glaring problem: thermodynamics. The second law states that entropy always increases, but a white hole seems to defy this by spewing order into the cosmos. Some physicists argue this makes them impossible, while others counter that white holes could be the end point of black hole evaporation. The final gasp of Hawking radiation after a black hole has nearly vanished. Whether real or just mathematical phantoms, white holes force us to confront a profound question: is the universe balanced between destruction and creation? If black holes are the end of matter's story, could white holes be the beginning of another? The answer might lie in the quantum fabric of spacetime itself, waiting to be unraveled. Black holes might be more than just cosmic vacuum cleaners. They could be the universe's backdoors, hidden passageways threading through the fabric of reality itself. The idea isn't as far-fetched as it sounds. Back in 1935, Albert Einstein and Nathan Rosen explored a radical solution to their own equations, uncovering the theoretical possibility of bridges connecting distant points in spacetime. These Einstein-Rosen bridges, better known as wormholes, would act like cosmic shortcuts, tunneling through the universe's folds. Picture spacetime as a sheet of paper. Bend it until 2 points touch, and a wormhole could stab through that connection, turning a journey of billions of light years into a stroll across the cosmic backyard. Now here's where black holes come in. Some theories suggest that the crushing gravity of a singularity might not be the end of the road. It could be the entrance to one of these bridges. If you could survive the trip, and that's a big if, you might emerge somewhere entirely different, another universe, another time, or even another version of reality. The catch: wormholes are notoriously unstable. According to general relativity, they'd snap shut faster than you could blink, crushed by their own gravitational forces. Unless, that is, you could prop them open with something exotic like negative energy or matter that repels rather than attracts. While we've never observed such materials, quantum mechanics hints they might exist in the form of vacuum fluctuations, tiny particles that pop in and out of existence with bizarre properties. But the multiverse connection goes even deeper. Some cosmologists, like Lee Smolin, propose that black holes could be cosmic nurseries, birthing entirely new universes inside their depths. Here's how it might work. When a star collapses into a singularity, the extreme conditions could trigger a quantum bounce, a rebound so violent it spawns a new space-time bubble, expanding into its own separate universe with its own physical laws. In this wild scenario, our own universe might have been born this way, a child of some long-ago black hole in another reality. It's a dizzying thought. Every black hole in our cosmos could be a lifeline to another, each with its own stars, planets, and perhaps even life. What does this mean for the soul of matter? If black holes are gateways, then matter isn't just stuff, it's a passport to infinity. The atoms in your body, forged in the hearts of stars, might one day cross a horizon and become the building blocks of another universe entirely. The iron in your blood, the carbon in your cells, could someday rewrite the laws of physics in some distant cosmic offspring. This isn't just poetry, it's a frontier of science where the boundaries between physics and philosophy blur. Whether wormholes or baby universes, these ideas stretch our understanding of existence, suggesting that matter's story doesn't end at a singularity. It might just be the beginning of another. For centuries, black holes existed only in the realm of equations and imagination, until technology finally caught up with theory, turning these cosmic phantoms into observable reality. The first smoking gun came in 1971 with Cygnus X1, a distant X-ray source in the constellation Cygnus. Astronomers noticed its strange flickering, a supergiant star orbiting something invisible yet so massive it had to be a black hole, devouring its companion's gas and heating it to millions of degrees in the process. This wasn't just a hunch. The data fit perfectly with predictions: an invisible monster roughly 15 times the sun's mass, warping space-time so severely that even its telltale X-rays were redshifted, stretched by gravity's grip. After decades of speculation, we finally had proof. Black holes weren't just mathematical ghosts, they were out there. Then came the game changer: LIGO detection of gravitational waves in 2015. When two black holes, each about 30 times the mass of our sun, spiraled into each other over 1 billion light-years away, they sent ripples through space-time itself. These waves weren't light or matter, but vibrations in the cosmic fabric, carrying a story written in gravity. As the black holes merged, their signals matched Einstein's predictions with uncanny precision, down to the final ring down, the aftershock of the newborn black hole settling into its shape. Suddenly, we weren't just seeing black holes, we were hearing them, eavesdropping on the universe's most violent symphonies. But perhaps no moment captured the public's imagination like April 10, 2019, when the Event Horizon Telescope unveiled the unthinkable, an actual image of a black hole's shadow. Not an artist's rendering, not a simulation, a real photograph of the supermassive black hole at the heart of galaxy M87, 55 million light-years away. The image revealed a glowing ring of hot gas circling the event horizon, with a dark void at its center, the black hole's silhouette carved into light itself. The achievement was staggering. It required synchronizing radio telescopes across the globe to create a virtual dish the size of Earth, all to capture a target smaller than a grain of sand on the moon. These breakthroughs didn't just confirm theories, they reshaped them. Every observation peeled back another layer of mystery. Gravitational waves revealed black holes could be far larger than we thought, merging in ways that defied expectations. The Event Horizon Telescope's image showed the shadow was slightly lopsided, hinting at the black hole's spin warping near by spacetime like a cosmic whirlpool. Even Cygnus X1, upon closer study, turned out to be heavier than initial estimates, challenging models of how such massive black holes form. What does this mean for our cosmic philosophy? Observation forces us to confront the limits of human intuition. Black holes shouldn't exist by everyday logic, yet there they are, bending light, shaking spacetime, and rewriting the rules. Each discovery is a reminder that reality isn't just stranger than we imagine. It's stranger than we can imagine. And as we push our instruments further, who knows what other impossibilities might come into view? The universe, it seems, is just getting started. Black holes don't just distort spacetime, they shatter our assumptions about reality itself. For centuries, materialism told us the universe is just a collection of particles bumping in the void, that everything from stars to human thought boils down to matter obeying fixed laws. But black holes laugh in the face of that simplicity. When matter crosses the event horizon, it's not just crushed, it's transformed into something that defies our definitions. If particles can be stretched into strings, smeared across horizons, or rewritten as holograms, then what is matter, really? The old idea of solid, independent stuff dissolves into a deeper mystery, one where information and relationships might be the true currency of existence. This forces us to confront a question that's haunted philosophers since Kant. Is reality fundamentally mathematical? Or is math just a tool we've invented to describe patterns we perceive? Kant argued that we never experience the thing in itself, only the shadows it casts on the walls of our cognitive cave. Black holes amplify this dilemma. Their singularities are zones where equations spit out infinities, screaming that our math has hit a wall. Yet their event horizons hum with precise, computable rhythms, obeying thermodynamic laws as if nature herself is balancing cosmic books. So which is the illusion, the messy, emergent world we see, or the pristine equations we use to explain it? Some physicists, like Max Tegmark, take the mathematical universe hypothesis literally. Reality is math, and black holes are just particularly complex equations playing out. Others, like Carlo Rovelli, see math as a map, not the territory, a brilliant but incomplete tool for navigating a reality richer than symbols can capture. The holographic principle blurs the line further, suggesting that the 3D world we experience might be a projection from a 2D surface, like a shadow puppet cast by deeper, invisible rules. So where does this leave us? If black holes teach us anything, it's that matter is more fluid, more mysterious than we ever imagined. The iron in our blood, the light from our screens, these aren't just static objects. They're dynamic knots in spacetime's fabric, shaped by forces we're only beginning to grasp. And that realization isn't just academic. It reframes how we see everything from quantum computers to consciousness itself. After all, if even a black hole's darkness pulses with hidden order, what other surprises might the universe be hiding in plain sight? Long before telescopes captured their shadows, black holes already haunted human imagination, not as scientific phenomena, but as mythic voids whispering of creation and oblivion. Ancient cultures spun tales of cosmic abysses that mirrored these mysterious objects. The Maori spoke of Tikor, the formless nothingness from which all life emerged. Norse mythology described Ginnungagap, the yawning gap between fire and ice where worlds took shape. These weren't just stories, they were attempts to grapple with the same existential questions black holes pose today. What lies beyond the edge? Can destruction birth something new? Fast forward to modern cinema, and black holes have become narrative powerhouses. Christopher Nolan's Interstellar didn't just visualize one, it weaponized its symbolism. The film's Gargantua, a swirling leviathan of light and shadow, wasn't merely a backdrop. It became a metaphor for sacrifice and love's transcendence, bending time like space-time itself. Compare that to the monstrous singularity in Event Horizon, where a black hole morphs into a literal helmet, echoing age-old fears of the unknown as something hungry and malevolent. Even Doctor Who's TARDIS treats black holes as both threat and gateway, playing with their dual nature as destroyers and doorways. But why do these cosmic oddities resonate so deeply? Perhaps because they embody paradoxes we recognize in ourselves. A black hole is a prison with no bars, a place where freedom and fate collide. It's Sisyphus's hill rewritten in cosmic scale, matter eternally falling toward an unreachable center. Artists and writers latch onto this tension, turning black holes into canvases for human angst and wonder. This cultural fascination isn't just poetic, it's practical. When scientists first proposed black holes, they faced skepticism as fierce as any mythic hero's trials. The idea that stars could collapse into invisible points seemed less like physics and more like legend. Yet here's the beautiful twist. Humanity's oldest stories primed us to expect such wonders. The same curiosity that painted gods riding chariots across the sky now fuels quantum telescopes probing event horizons. Our myths weren't wrong, just premature. So the next time you see a black hole depicted as a glowing vortex in a sci-fi film, remember, you're witnessing the latest chapter in a very old story. One where monsters and portals aren't just special effects, they're reflections of our endless drive to confront the darkness and decode its secrets. After all, isn't science itself a kind of myth-making, replacing dragons with singularities but keeping the awe intact? The abyss still stares back. We've just gotten better at blinking first. The next decade promises to revolutionize our understanding of black holes with instruments so advanced they border on science fiction. Take the Laser Interferometer Space Antenna LISA scheduled for launch in the 2030s. Unlike ground-based detectors like LIGO, LISA will float in space, forming a triangular array of satellites separated by millions of kilometers. This colossal scale lets it catch gravitational waves from supermassive black holes merging at the dawn of time, frequencies too low for Earth-bound instruments to hear. Imagine tuning into the universe's deepest bass notes, vibrations from collisions so massive they shake space-time itself. These echoes could reveal how the first black holes formed, whether they grew from dying stars or sprang fully formed from the Big Bang's chaos. But LISA isn't flying solo. Next-generation telescopes like the Vera Rubin Observatory and the Extremely Large Telescope will scan the skies with unprecedented precision, hunting for blinking stars' subtle flickers that might betray invisible black holes drifting silently through our galaxy. Others, like the Athena X-ray Observatory, will peer into the fiery disks around supermassive black holes, mapping how they warp light and devour matter in real time. And then there's the Event Horizon Telescope, which captured humanity's first black hole image. Soon, with new antennas added to its network, it could film a black hole's shadow as it evolves, watching how its fiery ring dances over months or years. These missions aren't just about sharper pictures, they're hunting for physics' holy grails. One tantalizing target, quantum gravity. When black holes merge, the resulting gravitational waves might carry faint imprints of spacetime's granularity, hints that reality isn't smooth but pixelated at the tiniest scales. It's like listening to a bell ring and deducing whether it's made of solid metal or a mesh of vibrating strings. Similarly, subtle twists in black hole shadows could betray exotic physics wormholes, extra dimensions, or even traces of dark matter's influence near the event horizon. Then there's the information paradox, the puzzle that's confounded physicists since Hawking. Future detectors might spot anomalies in how black holes evaporate, clues that information isn't lost but scrambled into Hawking radiation like a cosmic encryption. Others could find evidence for soft hair, the hypothetical quantum fuzz on event horizons that might preserve data like a celestial hard drive. Each possibility opens doors to wilder ideas, that black holes are quantum computers, or that the universe itself is a hologram. What's exhilarating is how much we don't know. Every answered question spawns 10 new ones, and that's the thrill of science. The tools we're building today will probe realities beyond Einstein's dreams, testing whether black holes are destroyers, transformers, or something stranger still. So stay curious. The universe has never been content with simple answers, and neither should we. You don't need a PhD or a billion-dollar telescope to explore the mysteries of black holes. Some of the most thrilling discoveries in astrophysics start with curious minds just like yours. Thanks to the digital age, the tools of the trade are more accessible than ever. Take Zooniverse, for example, a platform where anyone can sift through real telescope data, hunting for gravitational lenses or odd star movements that might betray hidden black holes. It's like being handed the keys to the universe's backroom, where your clicks could help uncover something textbooks haven't even written yet. If you're itching to visualize these cosmic beasts, software like Space Engine or Universe Sandbox lets you simulate black holes right on your laptop. Warp spacetime, fling stars into orbits, or recreate the epic collision LIGO detected, all while watching the physics play out in real time. These aren't just games, they're powerful engines running the same equations professionals use, stripping away the math and leaving pure, visceral wonder. For those who prefer their science hands-on, NASA's Open Data Portal is a goldmine. Raw images from Hubble, Chandra, and the James Webb Space Telescope are all there, waiting for you to process them. Ever wanted to colorize a black hole's accretion disk or measure the redshift of its jets? With free tools like DS9 or Aladdin, you can. It's the closest thing to piloting a virtual observatory, where every filter you tweak might reveal details even astronomers haven't spotted. And let's not forget the power of pure observation. On a clear night, even a backyard telescope can glimpse the aftermath of black holes' carnage. Point it at Cygnus X1's neighborhood, and you're seeing the very star whose stolen gas first proved these monsters exist. Or track the flares from Sagittarius A, our galaxy's supermassive heart, using public data from telescopes like the Event Horizon Telescope's archives. You're not just stargazing, you're witnessing the same cosmic dramas that reshape galaxies. What's beautiful about all this is how it mirrors humanity's oldest instinct, to look up and ask why. Centuries ago, people charted the heavens with nothing but naked eyes and stone tablets. Today, we've traded those tools for algorithms and satellites, but the hunger remains the same. Whether you're classifying galaxies on your phone or rendering black holes in VR, you're part of a tradition that stretches back to the first campfires where stories were told about the dark between the stars. The universe doesn't care if you're a 10-year-old with a telescope or a professor at Caltech. It whispers its secrets to anyone willing to listen. Black holes have been painted as cosmic vacuum cleaners in pop culture, devouring everything in their path with an insatiable hunger. But here's the truth: they don't suck matter any more than a star does. Gravity is gravity, whether it's coming from a black hole or the sun. The difference is intensity, not mechanism. If you replaced our sun with a black hole of the same mass, Earth's orbit wouldn't change. We'd just freeze in the dark. The real danger isn't some supernatural pull, it's getting too close. Cross the event horizon, and that's when the rules get weird. Another myth that black holes are rare, distant monsters. In reality, they're everywhere. Our galaxy alone could harbor over 100 million stellar mass black holes, the remnants of dead stars, and nearly every large galaxy, including our Milky Way, hosts a supermassive one at its core. Sagittarius A, the behemoth at the center of our galaxy, weighs 4 million times the Sun's mass, yet it's practically dormant, a sleeping giant. The universe isn't crawling with black holes because they're hungry. They're just there, like cosmic punctuation marks in the story of gravity. Then there's the idea that black holes are portals to other dimensions or time machines. While wormholes are mathematically possible, no evidence suggests black holes function this way. The tidal forces near a singularity would shred anything or anyone long before exotic physics could kick in. Even if you survived spaghettification, the extreme warping of time near the event horizon means you'd never make it out to tell the tale. The universe doesn't do shortcuts. It does physics relentlessly and without mercy. Perhaps the most persistent misconception is that black holes are eternal. Thanks to Hawking radiation, they evaporate just unimaginably slowly. A black hole with the mass of our sun would take 10 to the power of 67 years to vanish. That's a 1 followed by 67 zeros. For context, the universe is only 13.8 billion years old. So while black holes aren't forever, they might as well be by human standards. Debunking these myths isn't just about setting the record straight, it's about appreciating how black holes really work. They're not sci-fi plot devices. They're natural phenomena governed by the same laws that shape planets and stars. The more we demystify them, the more we uncover about the universe's grand design. And that's where the real magic lies, not in exaggerated fears, but in the awe of understanding. Black holes may be the universe's silent architects, shaping not just galaxies, but the ultimate fate of everything. Picture a future so distant that stars have burned out, galaxies have drifted apart, and the cosmos is a vast, cooling graveyard. In this frozen era, black holes might be the last active players slowly evaporating through Hawking radiation, their once imposing masses dissolving into faint puffs of particles. It's a poetic twist. The darkest objects in existence could become the final light, flickering out one by one until even their echoes fade. But this heat-death scenario isn't the only possibility. Some theories suggest a far more dramatic finale, where black holes aren't just relics but catalysts for cosmic rebirth. Take the Big Crunch, a hypothesis where the universe stops expanding and collapses back in on itself. In this scenario, black holes could merge into ever larger monsters, their gravity pulling everything toward a single, catastrophic reunion. Imagine all matter compressed into a seething, ultra-dense soup, a mirror of the Big Bang's fiery birth. Some models even propose this collapse could trigger a new universe, a cyclic rebirth where the ashes of one cosmos become the seeds of another. It's a dizzying thought. Black holes as cosmic recyclers, their singularities acting as portals to another beginning. Yet another possibility lies in the holographic principle. If black holes preserve information on their surfaces, could the entire universe, even in its dying moments, be encoded in some unimaginable way? The data of every star, every planet, every fleeting thought might not vanish but transform, like a book translated into a language we can't yet read. This isn't just philosophy, it's a challenge to our understanding of entropy and time. If information persists even in scrambled form, does the end truly exist? What ties these theories together is the role of matter itself. Whether crushed into oblivion, reborn in a new cycle, or encoded into some cosmic archive, the atoms that built galaxies and us are never truly gone. They're reshaped, repurposed, perhaps even remembered. The iron in your blood, the calcium in your bones, might one day swirl into a black hole's depths, only to re-emerge in some distant, unknowable future. That's the paradox of these cosmic abysses. They're both enders and alchemists, destroyers and potential architects of realities yet to come. The universe's final chapter isn't written yet, but black holes hold the pen. Science often walks a tightrope between discovery and danger, and nowhere is that balance more precarious than in black hole research. The idea of creating artificial black holes might sound like the plot of a disaster movie, but it's a real ethical dilemma physicists have grappled with. When the Large Hadron Collider first powered up, some feared its high-energy particle collisions might spawn microscopic black holes tiny enough to slip through Earth unnoticed or, in worst-case scenarios, grow uncontrollably. The scientific consensus: impossible. The energies involved are far too low, and even if one somehow formed, Hawking radiation would evaporate it instantly. But the fear lingered because the stakes are so unimaginably high. What if the math was wrong? What if nature had surprises we hadn't accounted for? This tension between curiosity and caution isn't new. Every frontier of science carries risks, from nuclear fission to gene editing. But black holes add a unique wrinkle. Their potential consequences are cosmic in scale. Unlike a lab accident contained to a single facility, a runaway micro-black hole could, in theory, consume the planet. The odds are astronomically low, but they're not zero. That sliver of uncertainty forces researchers to ask uncomfortable questions. How much risk is acceptable in the pursuit of knowledge? Who gets to decide? Scientists, governments, the public. The debate echoes early nuclear research, where the same minds who unlocked the atom's power also warned of its horrors. Yet halting exploration isn't the answer either. Black holes aren't just academic puzzles, they're keys to understanding gravity, quantum mechanics, even the origin of the universe. The data we gather could revolutionize energy, computation, or materials science in ways we can't yet predict. But with great power comes great responsibility, and the scientific community has learned hard lessons from past oversights. Modern particle colliders now include rigorous safety assessments, peer-reviewed by independent panels. Protocols exist to shut down experiments at the faintest hint of anomaly. It's a system built on transparency because the price of secrecy is distrust, and in science, trust is the currency of progress. What's striking is how these ethical dilemmas mirror the physics itself. Just as black holes warp space-time, bending light and time into paradoxes, they also distort our moral frameworks. They force us to weigh immediate risks against long-term rewards, to balance the hunger for discovery with the humility to acknowledge what we don't and can't yet know. Perhaps that's the most profound lesson. Science isn't just about answering questions. It's about learning how to ask them responsibly, ensuring that the light of knowledge never becomes a shadow we can't escape. Black holes aren't just the domain of astrophysicists, they're cosmic puzzles that ripple through unexpected corners of human knowledge. Take computer science, where the information paradox has become a goldmine for theorists studying data storage and encryption. The idea that black holes might preserve information on their surfaces mirrors cutting-edge research into holographic data storage, where three-dimensional information is encoded on two-dimensional surfaces. Tech giants are already experimenting with similar principles, packing more data into smaller spaces by borrowing mathematical tricks from black hole thermodynamics. It's as if the universe's most destructive objects are teaching us how to build better hard drives. Then there's biology, where extremophiles organisms thriving in Earth's harshest environments offer eerie parallels to hypothetical life near black holes. Near hydrothermal vents, bacteria survive crushing pressures and scorching temperatures that would obliterate most life. Could similar organisms exist in the accretion disks of black holes, where temperatures reach millions of degrees? While no scientist seriously expects fish swimming in plasma jets, the question reframes how we define habitability. Life as we know it requires liquid water, but near a black hole's event horizon, tidal forces and Hawking radiation might create bizarre pockets where exotic chemistry unfolds. Astrobiologists now study these edge cases to expand our search for life beyond Earth, proving that even the universe's most hostile corners can inspire biological breakthroughs. Even art and architecture draw inspiration from these cosmic phenomena. The spiraling patterns of black hole accretion disks appear in everything from ancient mandalas to modern concert halls, their fractal beauty tapping into some deep human fascination with ordered chaos. Architects have borrowed the gravitational lensing effect where black holes bend light into rings to design buildings that play with perception, using curved mirrors and warped surfaces to create impossible visual effects. What makes black holes so endlessly fascinating is how they refuse to stay in their lane. A single observation, like the first image of M87's shadow, sends shockwaves through philosophy, technology, and even theology. When disparate fields collide around these cosmic mysteries, that's when real breakthroughs happen. The next Einstein might not come from a physics lab, but from a programmer studying information loss or a biologist pondering life in extreme gravity. After all, the universe doesn't care about disciplinary boundaries. Why should we? This cross-pollination of ideas reveals something profound. Black holes aren't just objects in space. They're mirrors reflecting our collective curiosity, showing how one cosmic question can illuminate 1,000 earthly pursuits. Whether you're an artist, engineer, or gardener, there's something in their darkness that speaks to the heart of creativity itself. There's something undeniably spiritual about the way black holes capture our imagination, not because they confirm any doctrine, but because they echo the oldest human metaphors for the unknown. Across cultures and centuries, voids and abysses have symbolized both annihilation and renewal. The Hindu concept of Shiva's dance portrays destruction as a prelude to creation, while Buddhist philosophy speaks of sunyata, the luminous emptiness from which all form arises. Black holes, in their relentless gravity and paradoxical nature, tap into these primal themes without demanding belief. They are cosmic Rorschach tests, revealing what we project onto the darkness. Consider the event horizon, a boundary where time distorts and light bends back on itself. In many spiritual traditions, thresholds like this represent transformation, the moment before enlightenment, the crossing into the afterlife, or the dissolution of the ego. The parallel isn't literal, of course. A black hole won't grant nirvana, but the awe it inspires mirrors what mystics describe when grappling with the infinite. When the poet Rumi wrote, "You are not a drop in the ocean, you are the entire ocean in a drop," he might as well have been describing a singularity, a point where the ordinary rules of scale and substance collapse. This resonance isn't accidental. Both science and spirituality are human attempts to make sense of vastness using the language of their time. Where ancient stargazers saw celestial gates, we see warped space-time. The difference lies in method. One relies on revelation, the other on equations. Yet both can coexist without conflict. the physicist Carl Sagan once compared standing before the cosmos to feeling a tingling in the spine, a sensation indistinguishable from reverence. That tingling isn't about answers, it's about the humility of asking questions too grand for easy resolution. Perhaps the most poignant overlap is the theme of rebirth. Many cultures mythologize cyclical creation, from the phoenix rising from ashes to the Ouroboros serpent eating its own tail. Black holes, too, hint at regeneration. Hawking radiation suggests they aren't eternal. They evaporate, returning energy to the universe. Some theories even propose their interiors could birth new universes, turning destruction into genesis. Again, this isn't scripture, it's mathematics, but the symbolism is potent enough to stir something deep in us, a reminder that endings and beginnings might be two faces of the same cosmic coin. What's vital here is nuance. Drawing poetic parallels doesn't mean equating telescopes with prayer beads. Science seeks testable truths. Spirituality navigates meaning. Yet when a black hole's shadow appears on a telescope screen, or when gravitational waves hum their ancient song, it's okay to feel the weight of something transcendent. The universe, it seems, has room for both the measurable and the ineffable, for the precision of physics and the poetry of wonder. After all, isn't that duality the heart of being human? To count the stars while still dreaming what they are. Stephen Hawking didn't just study black holes, he made them speak. Diagnosed with motor neuron disease at 21 and given just 2 years to live, he defied medical odds while revolutionizing physics. Confined to a wheelchair and later relying on a speech synthesizer, Hawking's mind soared where his body couldn't. His greatest insight: black holes aren't truly black. In 1974, he proposed they emit radiation, now called Hawking radiation, slowly evaporating over eons. This shattered the idea that black holes were eternal traps, revealing instead their quantum whispers. But his brilliance came with controversy. The information paradox, his argument that black holes destroy information, sparked decades of debate, pushing physics to confront gaps between relativity and quantum theory. Hawking's later concession that information might escape after all showed his rare willingness to publicly rethink ideas, a testament to science's self-correcting nature. His life was as paradoxical as his work. A man who couldn't move reshaped our understanding of cosmic motion. Long before Hawking, Subrahmanyan Chandrasekhar faced his own battle against the scientific establishment. At just 19, aboard a ship from India to England in 1930, he calculated a star's fate if it exceeded a certain mass, now called the Chandrasekhar limit. His math showed that massive stars wouldn't fade gently but collapse into something unimaginable. When he presented his findings, Arthur Eddington, the era's leading astrophysicist, publicly ridiculed the idea, calling it stellar buffoonery. The backlash was racially tinged. Colonial-era science wasn't ready for a young Indian theorist overturning orthodoxy. Yet Chandra, as he was known, persisted. His limit became the foundation for understanding white dwarfs, neutron stars, and ultimately black holes. It took 50 years for the Nobel Committee to recognize his work, but his quiet perseverance redefined stellar evolution. Kip Thorne brought black holes from equations to pop culture. A key architect of LIGO, the gravitational wave detector, Thorne's work proved these cosmic monsters could collide and that we could hear the echoes. His collaborations with Carl Sagan on Contact and Christopher Nolan on Interstellar bridged science and storytelling. Thorne insisted Interstellar's black hole, Gargantua, be rendered with accurate physics, leading to discoveries about how accretion disks would realistically lens light. His textbook Gravitation, co-authored with Charles Misner and John Wheeler, became the Bible for generations of relativists. Thorne's genius lay in blending rigorous math with visceral imagination, whether predicting wormhole stability or mentoring students like Nobel laureate Barry Barish. These pioneers shared more than brilliance. They embodied science's human drama, Hawking's defiance, Chandrasekhar's resilience, Thorne's creativity. Their legacies aren't just papers and prizes, but a reminder that discovery thrives on curiosity and courage. As we stand on their shoulders, peering deeper into the abyss, their stories light the way, not just how to solve cosmic riddles, but how to keep asking them. Hollywood loves a good black hole, whether it's a swirling vortex of doom or a convenient plot device for time travel. But how often do these cinematic spectacles match the real science? Take Interstellar's Gargantua, painstakingly rendered by physicists to depict accurate gravitational lensing and time dilation. The glowing accretion disk bends light precisely as Einstein predicted, creating a halo effect that's as breathtaking as it is textbook correct. Compare that to Star Trek's black holes, which often act like cosmic whirlpools, sucking starships in with the urgency of a bathtub drain. In reality, a black hole's gravity behaves no differently than a star's until you cross the event horizon. No dramatic, sucking sound required. Then there's the infamous spaghettification, a term so absurd it sounds like a rejected pasta commercial. Films like Event Horizon turn it into a grotesque body horror spectacle, while others ignore it entirely. The truth, it's a real phenomenon, but not an instant one. A stellar mass black hole would stretch you like taffy long before you reach the horizon, while a supermassive one might let you drift in comfortably before the tidal forces shredded you. It's a nuance rarely captured on screen, where the rules of drama often outweigh physics. Even the concept of black holes as portals gets a Hollywood makeover. Doctor Who treats them as gateways to other universes, while Thor, Ragnarok turns one into a gladiatorial arena's trash chute. The reality is far less forgiving. Wormholes, if they exist, would require exotic matter with negative energy to stay open, something we've never observed. And crossing one, forget it. The gravitational forces alone would reduce any traveler to subatomic confetti long before they reach the other side. Yet for all their liberties, sci-fi deserves credit for sparking curiosity. Contact's wormhole sequence, though embellished, introduced millions to the idea of traversable cosmic shortcuts. The Martian's portrayal of orbital mechanics, while not about black holes, shows how accurate science can heighten tension without sacrificing entertainment. These stories aren't just escapism, they're invitations to dig deeper. When a viewer walks away from Interstellar Googling time dilation, that's a win for science literacy. The best sci-fi doesn't just entertain, it educates by osmosis. It takes the cold equations of relativity and wraps them in human drama, making the unimaginable tangible. So next time you see a black hole on screen, enjoy the spectacle, but let it fuel your wonder. Behind every Hollywood exaggeration lies a kernel of cosmic truth waiting to be uncovered. After all, reality, with its spinning singularities and holographic horizons, is strange enough without the special effects. What if Earth orbited a black hole instead of the Sun? Picture this, our planet locked in a delicate dance around a swirling abyss, its fiery accretion disk casting an eerie glow across our skies. The first thing you'd notice. Time itself slowing down, thanks to gravitational time dilation. A single Earth year near a black hole might stretch into decades for distant observers, meaning astronauts returning from a mission could find their loved ones aged far more than they have. And forget about seasons. The black hole's intense gravity would stretch our planet like taffy, triggering constant earthquakes and volcanic eruptions as tidal forces wrench Earth's crust apart. The only upside, that glowing disk of superheated gas could provide heat and light, though with radiation levels so lethal, we'd need to live deep underground to survive. Now let's tackle one of the most common questions. Can black holes die? The answer lies in Hawking radiation, the faint glow predicted by Stephen Hawking. Over unimaginable timescales, think trillions of years, black holes lose mass through this quantum process, shrinking until they vanish in a final burst of particles. But here's the twist: smaller black holes evaporate faster. A black hole with the mass of a mountain might last only a second, while a supermassive one could outlive the current age of the universe by a factor of 1 billion. Another burning query: could a black hole swallow the entire universe? Relax, it's impossible. Black holes are powerful, but their gravity follows the same inverse square law as any other object. They can only consume matter that ventures too close, like cosmic Pac-Mans with very limited reach. Even if one lurked at the edge of our solar system, planets would orbit undisturbed unless they strayed within its event horizon. Now for something truly wild. What if you fell into a black hole while holding a flashlight? From your perspective, the light would shine normally, but to an outside observer, it would redshift into invisibility as gravity stretches its wavelength to infinity. Your final moments would resemble a cosmic freeze frame, your image eternally lingering at the horizon while you, from your viewpoint, plunge into the unknown. These scenarios aren't just fun thought experiments, they're stress tests for physics, revealing where our theories hold up and where they crack under pressure. Got your own mind-bending black hole question? Drop it in the comments below. Who knows, your curiosity might just inspire the next big cosmic breakthrough. Visualizing a black hole is like trying to paint silence or sculpt darkness. It demands bending imagination around a phenomenon that defies every human intuition. These cosmic enigmas warp light, twist time, and erase the very rules of perspective we rely on to understand our world. Yet through an extraordinary alliance of science and art, we've transformed mathematical abstractions into breathtaking images that resonate across cultures and generations. Take the iconic first photo of M87's shadow, a fiery ring framing an absence so profound it feels less like an object and more like a hole punched through reality itself. This wasn't just a triumph of astrophysics, it was a masterclass in visual storytelling, where petabytes of radio telescope data became a visceral experience anyone could grasp. The collaboration between artists and scientists here is nothing short of alchemy. When the Event Horizon Telescope team needed to translate their findings into something comprehensible, they turned to specialists like Leah Halloran, whose fluid, luminous paintings capture the dynamism of cosmic violence without sacrificing scientific rigor. Or consider the work of digital artist Alvaro Gracia Montoya, who uses real astrophysical simulations to animate black holes as swirling, three-dimensional storms of light and shadow. These creators face a unique challenge: how to depict an object that, by definition, can't be seen. Their solutions, whether through exaggerated accretion disks, gravitational lensing effects, or strategic color palettes, reveal as much about human perception as they do about relativistic physics. What's fascinating is how these visualizations evolve alongside our scientific understanding. Early depictions, like the flat, funnel-shaped holes in 1970s textbooks, reflected limited computational power and nascent theories. Today's renderings, powered by supercomputers running general relativity equations in real time, show space-time as a shimmering fabric dimpled by rotating singularities, their ergospheres dragging the very universe around them like cosmic whirlpools. Games like Space Engine and films like Interstellar have democratized these visions, letting millions explore black holes from their couches with unprecedented accuracy. Yet every artistic choice carries philosophical weight. Should a black hole look menacing or majestic? How do you color-code temperatures in an accretion disk without misleading viewers about its actual hues? Even the decision to portray the event horizon as a sharp boundary, when quantum mechanics suggests it might be a fuzzy, particle-teeming zone, sparks debate. These aren't just technical quibbles, they're conversations about how we mediate between the knowable and the incomprehensible. The most profound takeaway isn't the images themselves, but what they represent: humanity's refusal to be intimidated by the universe's grandeur. From Stone Age star maps to quantum-rendered singularities, we've always used creativity to bridge the gap between observation and understanding. When a child sketches a black hole with crayons or a programmer models one in VR, they're participating in the same timeless tradition, turning wonder into wisdom, one impossible depiction at a time. Black holes might seem like the last place to search for signs of life, cosmic shredders where matter meets its doom. But what if advanced civilizations see them not as threats, but as tools? Imagine a society millions of years ahead of us, harnessing the unimaginable energy of an accretion disk. The superheated plasma swirling around a black hole emits enough radiation to power entire galaxies. A sufficiently advanced species could build Dyson-like structures to capture that energy, turning a destructive force into an engine of creation. Some theorists even suggest they might use the extreme gravity for slingshot maneuvers, flinging ships across interstellar distances at relativistic speeds. The concept isn't pure fantasy. Physicists have calculated how a black hole's ergosphere, the region outside the event horizon where spacetime itself is dragged along, could be mined for energy through the Penrose process. It's the ultimate high-stakes engineering project. Tap into the universe's most violent phenomena or risk being torn apart by tidal forces. This raises a haunting question tied to the Fermi paradox. If black holes are such potent resources, why haven't we detected any signs of civilizations using them? One possibility is that harnessing singularities is so perilous that even advanced species eventually succumb to catastrophic accidents. Or perhaps civilizations that reach this level of mastery become unrecognizable to us, their technology blending seamlessly with natural astrophysical processes. The eerie absence of obvious megastructures around known black holes might imply that the universe is still too young for life to have achieved such feats, or that we're simply not looking in the right way. Radio telescopes scanning for artificial signals might miss a civilization communicating through modulated gravitational waves or neutrino pulses. Then there's the darker hypothesis: black holes could be the universe's ultimate waste disposal. A hyper-advanced society might use them to contain runaway nanotechnology or dangerous experiments, tossing existential risks into the abyss where they can never re-emerge. It's a chilling thought that the silent voids dotting our galaxy might be cosmic landfills, the graveyards of civilizations that gambled with forces beyond their control. Yet amid these speculations lies a deeper truth. Black holes remind us that the universe is stranger than our boldest imaginings. Whether they're unclaimed engines of destiny or silent tombstones, their very existence stretches the boundaries of what's possible. The fact that we can even contemplate these questions peering across the abyss with math and curiosity is a testament to life's ingenuity. So while we may never find aliens riding the event horizon, the act of wondering connects us to something profound. The cosmos doesn't owe us answers, but it invites us to keep asking, and in that endless questioning we touch